It followed the same trend as ionization energy, right? So if we go from period 7 to period 1, what happens to electronegativity? It doesn't get lower, it gets higher, right? So it follows the same trend if we go from down to up, right? On the column, it gets, electronegativity increases the same way ionization increases with that trend, right? So electronegativity increases as we go from period 7 to period 1, as we go up the periodic table. And what about going from group 1 to group 8 across the columns? It gets bigger as well, right? So the electronegativity increases. And so electronegativity, that's the periodic trend itself, same as the ionization energy. Ionization energy was, again, how hard it was to ionize one of the valence electrons for the atom, meaning to bump it off the atom. How much energy do we have to put in? So it follows the same trend as ionization energy, and maybe using that rationale a little bit, what do you guys think electronegativity is? What does the property electronegativity represent? It has to do with the bonding, right? So it has to do something with the behavior in bonding between atoms and with electrons, right? So it has to do something with, how it bonds to the electron and how that atom bonds to other atoms. Right? Is a more electronegative element have more electron density or less electron density? Does it share more of the electron sublevels and energy levels, or does it have less for a more electronegative element? If we were using the analogy I used last time was the tug of war, right? Two people pulling on the electrons in the bonds. So electronegativity was the how much an atom will pull electrons to itself in a chemical bond, right? So in the tug of war analogy, the more electronegative element is the stronger person, right? They're pulling the rope more, they're pulling the electrons in the bond more, so that the electron density is unevenly shared between these atoms, right? So if we looked at fluorine and hydrogen, and let's say they're in a bond, and this represents the electron density, right? This highlighted part, and the highlighted part for hydrogen is there. Fluorine holds a lot more of the electrons in the bond than hydrogen does. Why? Because it's a more electronegative element. It likes to pull those electrons more to itself. Ionization energy said, oh, well, the electron's closer to the nucleus, so it holds that more tightly. In the same way, for a given higher nuclear charge with the energy levels, right, it'll pull more electrons to surround it, right? And so when we do that, what happens to the charge on the fluorine atom there? Remember, we get a partial charge, right? Because we have, so it was that lowercase delta and a minus was a partial charge. Because we have more electron density around it than usual, right? But it's not like we took the full electron. It still is shared somewhat with the hydrogen. So we took a lot of the electron density, so it has slightly more, but it doesn't have a full charge, right? Because it's only sharing the electron unevenly. It hasn't transferred the electron from the hydrogen to the fluorine completely, right? So it has a partial negative charge. Why? Because electrons carry negative charge, and this has more of the electron around it. And what about the proton? What happens to the proton? Does it have a partial charge too? Yeah, and that's partial what? Partial positive, right? Because this one, it usually has more electron density around it, but fluorine is taking it away. It hasn't completely taken all of the electron away. So only partially the electron is still, we could say, orbiting that hydrogen, right? So it has less than the usual amount to neutralize it, right? Usually we need an equal amount to neutralize it perfectly. It has slightly less than that, so it's slightly positive in its character. And that gives rise to this symbol right here, which was the the dipole in the molecule, right? And the dipole is what made the molecule polar or nonpolar, or the bond polar or nonpolar, right? It goes from positive to negative, and so that gives a dipole in the molecule. All a dipole is just an imbalance of charge. So we classified these bonds based off of the electronegativity. Electronegativity difference gives rise to a dipole, and then we gave some actual values on how we would classify these bonds, right? If we have an electronegativity difference of 0, right, how did we classify that bond? I'm gonna go, am I good to go to the next slide? Is anyone still writing? Right, if En is equal to 0, that bond how did we classify that bond? Is covalent, and specifically nonpolar covalent, right? Because the difference in electronegativity, right, so sorry, this should be a delta. The difference in electronegativity between the atoms in the bond is 0 because they're, for example, we have two hydrogens bonded to each other. They both pull on the electrons the same, it shouldn't be polar. If the electronegativity difference is 0, then they both are pulling on the electrons equally, so the bond is nonpolar, and it's covalent because they're sharing bonds. If we were between 0 let me write that a little neater. If we're between 0 and 1.7, how did we classify that bond? Right, and we said if we look these values up, sometimes that 1.7 shifts between 1.7 and 2.1, depending on what textbook you're looking at or what atoms are there. But how did we classify that bond? Yep, that was a polar covalent bond. Right, now we're in that special range where there's a difference in electronegativity, where one of the atoms is pulling on the electrons harder, right? So the density of the electron shared between them is around one atom more than the other. So we call that a polar covalent bond. And if the change in electronegativity was greater than 1.7 to 2.1, how do we classify that bond? That should be ionic, right? Because at this point, the electronegativity difference is so large that one atom says, I'm just going to rip that electron off of you. I'm not going to share it at all. I'm just going to pull that electron out of myself to look like a noble gas, and we're going to have an ionic bond, right? So this was a full transfer of electrons, right? In both of these cases, we share electrons. The difference between polar and nonpolar is one is shared equally. For nonpolar and polar, we share them unequally. All right, so we use this periodic trend, right? The trend we get because of the nice organization of how things are in the periodic table, which we used atomic structure to understand why they're organized that way. Those lead to emergent properties like electronegativity, ionization energy, and we can use that to predict the type of bonds it'll form with other atoms. And we can classify those. All right, any questions on ionic covalent bonding, polar, nonpolar, or electronegativity? Okay, and then we ended the discussion talking about how to represent molecule, representations of molecules, and we didn't get very far into that. And how are we going to represent molecules? Does anyone remember? For Lewis structures, right? Using Lewis structures. And dots, what did the dots represent? Valence electrons. And then dashes or lines, what did those represent? Shared electrons or bonds, right? These were covalent bonds between atoms. Covalent bonds between atoms. Right, so these were the covalent bonds between atoms. That's what we use the lines to represent. And we talked about, well, if we, look at the electronic structure of atoms, right? The valence electrons are the ones involved in bonding, and that gives the atom its personality, right? That's what tells us how it's going to interact with other atoms. The protons, that gives us the elements what? What does the proton, number of protons for an element tell us? Who remembers? What does the number of protons for an element tell us? Right, if it's a neutral atom, that'll tell us how many electrons we have in the element as well, right? But if I said, give me an element with 12 protons, what element is that? Magnesium, right? So the protons give us the identity of the element, right? As soon as we change the number of protons, we're no longer magnesium. If we have 11, now we're sodium, right? If we have 13, now we're aluminum, right? So the protons give us the identity. Electrons give us the personality of the atom. And so Lewis structures, we're looking at how does the valence electrons, which give us the most personality, behave when they interact with other atoms? How are we going to form bonds and molecules with that? And that'll ultimately allow us to find then the shapes of these molecules, right? And so we talked about a couple things, how Lewis structures based off of the valence electrons, that tells us the preferred number of bonds that we'll form. So this will be useful, for example, once we get familiar enough. If I see a carbon, I know that's probably going to have 4 bonds total. And I know for sure it will. If we have nitrogen, it'll probably form 3 bonds. Oxygen, 2 bonds, fluorine, 1 bond, right? And how do we know that? Well, based off of the group, right? Here's X just represents any arbitrary element. It could be fluorine, chlorine, iodine, whatever. They each have 7 dots around them, which means they have how many valence electrons? 7 valence electrons. So that's all the group 7 elements are all going to look like this Lewis symbol, right? Group 6, they're all going to look like this for that Lewis symbol. You just change the element from either oxygen to sulfur to selenium to telluride, and then group 5 is going to have 3 bonds preferred, and then this is going to be the Lewis dot symbol. So same for nitrogen, phosphorus, arsenic, antimony, and same thing for carbon, silicon, right? So that's based off of the group number, tells us the number of valence electrons. That tells us the number of bonds that will most likely form. All right, so this would be a quick way that we can look at something and kind of guess how the structures is going to end up looking. And this is going to be for covalent molecules, right? So ionic compounds, we're not really going to be drawing Lewis structures for, because we would just draw 2 Lewis symbols right next to each other. They don't share electrons with each other. And then we also discussed the existence of lone pair electrons, right? So anything that isn't used in bonding, so the group 5 elements, for example, like nitrogen, you're always going to have 2 electrons left over. Those exist as what we call a lone pair on the electron. They're important for determining the shape of the molecule still, but they aren't involved in bonding at all, right? So in the orbitals, the sublevels, these electrons still exist, but they haven't started to bond with any other atoms. All right, so these are all there's a lot of terms that go into understanding Lewis structures, right? The lone pairs, the dash electrons, valence electrons, and today we're going to spend a lot of time talking about how we actually draw these Lewis structures from these atoms. And so the Lewis structure, kind of the general rule of thumb, there are exceptions to this rule as there is with everything in chemistry. They must satisfy what rule? Octet rule, right? And the octet rule says what? We want to have 8 electrons around each atom with the exception of either hydrogen or helium because they only have the one S sublevel. But it means we want to have 8 electrons around them total because 8 electrons, we look like what? Noble gas, right? If we look like a noble gas, that means we're in like the most stable conformation we can have, right? Because the filled subvalence shell is what every atom is trying to go on. So the exception is going to be hydrogen or helium, right? And these form a doublet. So they'll be happy with just 2 electrons around it. So the exception is going to be hydrogen to that rule. And like I said, there's also a lot of other exceptions. For our class, we're not gonna worry about the exceptions, right? Once you start adding d orbitals and stuff, you can get a lot of exceptions to the rule. So most likely we're gonna be focusing on elements that are made from period 3 and lower, right? So period 3, 2, and 1. And so how these form, right, is that these two electrons, we get one from each hydrogen, right? So I'll draw it a little differently down here. Each hydrogen is in group what? 1, right? So it has how many valence electrons? It has 1. Let me just grade myself in the classes, right? It has 1 valence electron each, which is represented by 1 Lewis dot on the hydrogen atom. When we go to form a bond, these valence electrons now get shared with each hydrogen atom. So now we replace the 2 dots with a line or a dash between them. And now each electron is being shared with both hydrogens. So instead of having only 1 electron around it, now each hydrogen is how many electrons around it? 2, right? Because each hydrogen has contributed 1 electron to this covalent bond. And now both of those electrons are orbiting or circling both hydrogens now, right? So now, instead of only having 1 valence electron, the outermost shell for each hydrogen has 2. The shape of the shell and the energy level looks a lot different now because we have this extra hydrogen there, but now it has 2 electrons around it at all times, right? So now it looks like what element? Helium, right, which is a noble gas. So that's why hydrogen forms a doublet. It's happy doing that. Here we have 2 fluorine atoms, right? Fluorine isn't hydrogen, so it's going to want to satisfy the octet rule instead. And so fluorine is going to have how many Lewis dots around it? 7, right? Because it's in group 7, right? So if it has 7 dots around each fluorine. And I'm drawing it like this beforehand because I know where I want the bond to form, right? And so before they bond to each other, each fluorine atom looks like this. When they come together to form a covalent bond, each one donates a single valence electron to this covalent bond, right? So each one has picked up 1 new electron, right? And so now instead of having 7 electrons around each fluorine atom, we have how many? 8, right? So now we've satisfied the octet rule. So then this goes to fluorine. And then we still have all of these other lone pair electrons around the fluorine. This structure right here doesn't show them, but these ones still exist around each fluorine. Right, so that tells us that we have how many electrons around this fluorine? 8. If we count it, we have 1, 2, 3, 4, 5, 6. Each Lewis dot represents 1 electron, so there's 6 there. And then how many do we have in the bond? 2, right? So 7, 8. So that's where we get the total 8 from. So it's a common mistake I see a lot, is that we forget that there's 2 electrons in a bond. In this bond, that gives 2 electrons to this fluorine and 2 electrons to that fluorine. Why? Because these are sharing those electrons now, right? So we're sharing those electrons, which is why both of them have 8 around them. All right, so each one is going to satisfy, each element, for the purpose of our course, is going to want to have 8 electrons around it to look like a noble gas, with the exception of hydrogen, which is going to form a doublet. It's happy with just its 2 electrons because it looks like helium, right? Which is why we don't have any of the Lewis dots around the hydrogen. All right, any questions on the octet rule? I'm sure we'll get deeper into this and we'll find. We'll get some questions for sure. And so again, non-bonding electrons are displayed as lone pair electrons. And the bonding electrons, those are going to be shared between both atoms in the line, right? So how many electrons does this hydrogen have around it? 2, right? Because it has one bond attached to it. That means that this has 2 electrons that are around it. So it satisfies the doublet, so that hydrogen is happy. What about this nitrogen? How many electrons does it have around it? 8, right? Because it's 2, 4, 6, because there's 3 bonds attached to it. 7, 8 electrons because of the lone pair that's there. Right, so this has 8 electrons, so it satisfies the octet rule. How would I draw the Lewis structure for me here? Well, instead of what they have here, I would have each hydrogen has 1 valence electron, nitrogen has 5 valence electrons, and each lone valence electron for the nitrogen and the 1 valence electron from the hydrogen come together to form the bond. So that goes there, that goes there, and there. And then that's how we get to this final structure. And we'll talk about the process in doing that. But right now we're just learning to count the number of valence electrons and see if these satisfy. Hydrogen satisfies the doublet, and then nitrogen satisfies the octet rule. Right, so usually, this is the more kind of canonical or the standard way that people will draw this before they complete the Lewis structure. I like to draw them separated a little bit like this, so I can show the movement of the electrons into the bond. It highlights that, okay, each one is contributing an electron to form that covalent bond. And the same thing for carbon. Carbon's in group what? 4, right? So how many bonds does carbon like to form? 4 bonds, right? It has 4 valence electrons, it likes to form 4 bonds. Remember, carbon, group 4 likes to form 4 bonds, group 5 likes to form 3, group 6 likes to form 2, and group 7 likes to form 1 bond, right? So those are the kind of bonding trends. You don't have to memorize them. If we go through the process of drawing the Lewis structure, that'll come out naturally, but it's just another way to kind of check that you're on the right track. And so each hydrogen contributes how many electrons to this covalent bond? It contributes 1, but there is 2 electrons around the hydrogen, right? Because now it has a bond attached to it. And how many electrons are around this carbon now? 8, right? Because each bond has 2 electrons, right? So 2, 4, 6, 8. So carbon satisfies the octet rule. Each hydrogen satisfies the doublet, right? So that satisfies the octet. All right, so that's how we can look at a Lewis structure and understand that everything is satisfying octet or doublet rules. And so how do we actually draw a Lewis structure? So the first thing that you can do is you can count the number of electrons in the structure. This is an important step if we are trying to draw, like polyatomic ions. In general, the number of valence electrons, if I don't give you a charged atom, is we can just draw the Lewis symbols for everything. So this is more important for drawing charged molecules. And so this means counting up all the valence electrons. Right, so for all the valence electrons in your molecule, you count them up and add them up, and that gives you the total number of electrons. And this is just good to keep in your mind so that at the end, you should have the total number of electrons that you started with, right? They should be accounted for either in lone pairs or in bonds inside the molecule. And so similarly to when we were naming things, right, we put the most metallic element in this first, right, when we name stuff, that's how we name them. In a Lewis structure, we're going to draw a skeleton structure, which means we're just going to draw each Lewis symbol with the valence electrons, right? So this is the Lewis symbols with the valence electrons. That's what our skeleton structure is going to be. And we're going to put the most metallic element in the center. All right, so that's the general trend, is usually the most metallic element is going to be in the center. And if we have the most metallic element, we talked about the other periodic trend that we use to classify bonds. If something's most metallic, how would we describe that in terms of electronegativity? The least electronegative, right? So this would be the least electronegative, right? So the most metallic or the least electronegative element in the center. Generally, halogens and hydrogens are going to be terminal, which just means on the outside. So those are going to be on the outside. And nature likes to be symmetric, right? So nature likes things to look pretty in general. That's how things with energy just tend to work out. So if you're, given a molecule that has 1 carbon and 4 hydrogens, you're probably not going to have 1 hydrogen at the center, 3 on the outside, and then 1 hydrogen on the outside, right? So if we look at something like CH4, H, 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 we'll find other ways to know that this structure doesn't satisfy all the rules that we need. But if we were looking at the symmetry between these 2 molecules, which one looks prettier to you? Left or the right? The left, right? Because it has symmetry, meaning that if I rotate this, it looks the same. If I rotate this the other way, it looks the same. If I flip it around, it looks the same, right? It makes kind of more logical sense. Like our brains are trained to recognize patterns and stuff. That one looks like it follows a pattern, where the other one kind of looks jumbled up a little bit, right? Like we know if we put this carbon in the center, that'll be a more symmetric molecule than putting a hydrogen at the center there, right? But like I said, we'll find other rules to make sure that this doesn't end up happening. But in general, if you're looking at a starting point, symmetry is important, right? So this is not symmetric. And then if we have something like an oxyacid or an acid of some sort, generally you have a hydrogen attached to an oxygen. We'll talk more about that when we go over acids and bases later in the semester. But if you're given a Lewis structure that is an acid, you'll have a hydrogen that's attached to one of the oxygens as well. So this is how your first step. You're going to draw your skeleton structure. And then, once you draw your skeleton structure, you're going to connect the terminal atoms to the central atom, right? So if you have something like the molecule that we had before, which was CH, right? This is our skeleton structure. Right, our skeleton structure, we put the least electronegative or the most metallic element in the center. That's going to be carbon in this case because hydrogen likes to be terminal. We draw the valence electrons for each atom in our skeleton structure. And now we're going to connect the outer atoms to the central atom. We can just draw a line between the 2 dots. Like I said, I like to draw the arrows to show that each atom is donating an electron to be shared with the other atom. Right, so each one here is going to donate an electron to the bond between these atoms. So this becomes C bonded to 4 different hydrogens. And then we distribute the electrons to achieve the octet rule. If we draw the Lewis structure or the Lewis symbols in the first step, or in the skeleton structure, so in the second step, then you're not going to have to distribute electrons after this. This is important if we have charged atom or charged molecules. Molecules. And another way of saying this rule is that we have to make sure that we have the same number of electrons that we started off with. Right? So if we started off with 36 electrons in our molecule, 36 valence electrons, then we need to end with 36 electrons total. So we're going to end with the same number of valence electrons as we started with. If you find that you're violating the octet rule, right? So if we violate the octet rule, or for hydrogen, the doublets, or we have a different number of electrons that we started with, then we need to redistribute the electrons. And so the only way that we can redistribute electrons without violating anything is either taking them out of bonds or putting them into bonds, right? So this is can only do by taking electrons in or out of bonds. So we can only do that. We're putting electrons in or out of bonds. In the most common scenario you're going to see this is when you violate the octet rule. And usually what that means, if we started our skeleton structure right, that means that we need to create another bond somewhere, is usually what that happens. Or our initial skeleton structure wasn't a good guess, and we have to start by rearranging the atoms in that case. So in drawing Lewis structures, a lot of it just comes from practicing this enough times to make sure that you get it right. And you'll start to see patterns based off of the groups that each of the elements are in the type of structures they're going to form. All right, so that's a process to making the Lewis structure. So let's go through and see actually how we apply this now. Right, so let's look at H2O. So H2O is just water. How are we going to draw the Lewis structure for water? So usually we put the least electronegative element at the center. However, hydrogen likes to be where? On the outside, right? Hydrogen likes to be terminal. So we're going to put oxygen in the center here. And then we're going to draw the Lewis dots, which is the number of what for oxygen? Valence electrons. And then we're going to put hydrogens around it and draw the number of valence electrons for those elements too, right? So first we're going to draw the skeleton structure. And we can also count the total number of valence electrons. So if oxygen is how many valence electrons? 6. And then hydrogen has how many?
4. Oh, wait,
1, right? So hydrogen has 1, oxygen has 6, and we have how many hydrogens? So how many total electrons should we have? 8 total electrons, right? 8 total electrons because there's 2 hydrogens with 1 valence each and 1 oxygen with 6 valence electrons. Right, so that's how we get 8 total electrons. So we put oxygen in the center. We know it has 6 dots around it. So the same way we fill up, I put the right amount. We fill up sublevels with hundredel, each one in each orbital. Generally, you can go around in a circle and put 4 dots at each side of the element and then go back and pair them. I draw it this way just because I know it'll be easier to make the Lewis structure, but you don't have to. Meaning that I put the 2 paired electrons on top and bottom and 1 lone electron on each side. And then hydrogen has 1 valence electron. And so now, after I've drawn my skeleton structure, I'm going to connect the terminal or the outer atoms to the central atom by putting 1 electron each from each atom into a bond. So I've connected, right, connected the atoms. And so now I need to check to make sure that the octet or doublet is satisfied for all the appropriate elements. And if it is, then I'd have a valid Lewis structure for the molecule. So in this case, how many electrons are around this hydrogen here? How do you know there's 2 electrons there? Yeah, because we have a bond here, right? And a bond means that there's 2 electrons around this hydrogen. Any bond attached to that element says there's 2 electrons around it. What about this hydrogen here? 2 because it's attached to a bond, which means that there's 2 electrons in this bond and they are also around this hydrogen. And what about oxygen? 8, right? Because we have how many from each bond? 2 from each bond. So we have 2, 4, 5, 6, 7, 8 electrons total around this oxygen, right? So we check the octet rule. Octet or doublet. Hydrogen has 0 dots, 1 bond, which means that we have 0 electrons from dots, 2 electrons from a bond, so we have 2 electrons total. It satisfies the doublet, right? Oxygen, we have how many dots around oxygen? 4 dots, which represents how many electrons? 4 electrons. And we have how many bonds? 2 bonds. And that represents how many electrons? 4 electrons. So we have 8 electrons total around it, so it satisfies the octet. All the octet and doublets are satisfied, which means that this is a valid Lewis structure. All right, so this is okay for our Lewis structure. All right, so the knowledge we need is how many valence electrons are around each element, which one is either going to be the least electronegative or the most metallic is what we'll put in the center, unless there's halogens or hydrogens there. And then we need to know how to connect the outer and the central atom. All right, any questions on this example? All right, so let's look at one that may be a little bit more complicated now, right? So you have this molecule. Does anyone know what this molecule is called? Carbon dioxide. We can name it because we have the tools to. Most metallic element goes first. Carbon. Oxygen is the second element. So we replace the ending of oxygen with what? Ide. And then do we need a prefix? What kind of molecule is this? Ionic or covalent? Covalent, right? Because it's between 2 nonmetals, right? Also, we're drawing Lewis structures. Can't draw Lewis structures for ionic compounds. Well, we can, but we're not going to do that. So this is going to be a covalent molecule. And for covalent molecules, do we need prefixes? Yes or no? Thumbs up, thumbs down. We need prefixes for covalent molecules. Why? Because we need to know how many of that element is in the molecule. For ionic compounds, we don't because the charges is what tell us how many there are. This is covalent though, so we need the prefix. So this is called carbon dioxide, right? That's the prefix that tells us we have how many oxygens? 2, right? And we replace the ending with ide because it's the more electronegative element or the least metallic element. All right, so what element is going to go in the center in this case? It should go carbon, right? Because it's more metallic or less electronegative than oxygen. How many valence electrons does carbon have? 4, right? Because it's in group 4. And on the outside, we're going to put what elements? Oxygen. And oxygen is how many? 6, right? So it should have 6 dots around it. 1, 2, 3, 4, 5, and 6. And it's going to be the same thing on the other side. right? So drawing the skeleton structure, I have all my valence electrons accounted for. I can go up and count all of them to make sure that they add up at the end to the same number of valence electrons. Oops, I drew this one a little off. Right, and after I draw my skeleton structure, what do I need to do? Connect the outer atoms to the central atom, which means that each one is going to donate 1 electron to a bond between them. All right, so I'm going to connect them. I get oxygen to carbon, oxygen, then 2 electrons there. So once I've connected my outer and my central atoms, what do I need to check? The octet rule, right? So let's check the octet rule now. So check octet. Let's look at each oxygen is the same, so we only need to look at one. Oxygen is how many dots around it? In this molecule, how many dots are around this oxygen? 1, 2, 3, 4, 5. Right? We have 5 dots around it. Does everyone see why there's only 5 dots? Right, there's a 1, 2, 3, 4, 5 dots, which means that dots are only representing 5 electrons here. Right, so we have 5 dots, which is how many electrons? 5 electrons. How many bonds are attached to oxygen? 1, right? So we get 1 bond, and that represents how many electrons? 2. So we add these up, and how many electrons are on this oxygen? 7 electrons. So does it satisfy the octet rule? No, it doesn't, right? So it doesn't satisfy the octet rule, which means we need to redistribute electrons either into or out of bonds. If we distribute anything out of bonds right now, it's going to detach our molecule, right? So that tells us we have to put electrons into a bond somehow. But before we do that, let's just double check and see if the octet is going to be satisfied for carbon. I can tell you because oxygen's not satisfied, we have to adjust the molecule somehow. But let's check it for carbon as well. So for carbon, how many dots are around carbon? Yep, 2 dots. Right? We have 1, 2. So we have 2 dots around the carbon. And that's how many electrons? 2 electrons. And how many bonds are attached to carbon? 2 bonds, right? So 2 bonds, which is how many electrons? 4 electrons. So how many electrons do we have around carbon? 6 electrons, right? So this also doesn't satisfy the octet rule. All right, so both of these don't satisfy the octet rule, which means that we need to redistribute electrons somehow to see if we can satisfy that for all of these molecules. Does anyone have any idea how we can do that? Oh yes, okay, so a lot of people said it. So we can make a double bond from this, right? Which means we take 1 valence from each of the atoms again, and we donate to form another bond between these elements, right? So we're gonna adjust the structure. I'm just gonna draw it down here again. We have C or O, O, and each of these are going to come together to form another bond between the carbon and each oxygen, right? So this then becomes O, 2 bonds now between the carbon and each oxygen. All right, so we've adjusted the structure. The only way we can adjust it is by moving stuff in or out of the bonds that we have in our structure. If we destroyed any other bonds in the previous one, then we would have broken up the molecule, right? So that told us we probably need to make another bond between carbon and each of these. And so, how many bonds? Let's check the octet rule for carbon now. So we need to check the octet rule again to see if it's satisfied. For carbon, how many bonds are there? 4 bonds. And how many dots? 0, right? So how many 0 dots? How many electrons are there in dots? There's 8 total, but how many electrons in dots? 0 electrons, right? So we're a little ahead of ourselves, but that's fine. And then 4 bonds is how many electrons? 8, right? Because each bond has 2 electrons. So we have 8 electrons, and we get 8 electrons total. That means that we satisfy the octet rule for carbon in this case. Let's check each oxygen now. Oxygen is how many dots around it? 4. 1, 2, 3, 4. So we have 4 dots around each oxygen. So 4 dots represents how many electrons? 4 electrons. How many bonds are there attached to oxygen? 2. 2 bonds represents how many electrons? 2 times 2 equals 4. So we have how many electrons total around oxygen? 8 electrons. So we've satisfied the octet rule for both the oxygens and the carbon. That means that this is our valid Lewis structure for carbon dioxide. All right, so this is a little bit more challenging. Why? Because when we first attach them, we don't get a valid Lewis structure right away. So we have to realize, okay, I need to now redistribute electrons either in or out of bonds to then satisfy the octet rule for all these atoms. We don't have any hydrogens, so there's no doublets to satisfy here. It's just carbon or any heavier elements, which we need octet around each of them. All right, any questions on this example? No. Mm-hmm.
Is there ever gonna be a time where there's like, it's not in eights, like 8, 16, when the electrons will there be like, I don't know how to ask the question.
When you, like you're saying, when I counted the total electrons in the beginning, I had a multiple of 8.
Yeah, will it ever not be a multiple of 8?
Yeah, there'll be times when it's not a multiple of 8, even if, right? So you can have an odd number, not an odd number, but an even number of electrons that you're starting off with that aren't directly multiples of 8 because some don't start off with an even number, right? So we just need to make sure that we have each element surrounded by 8 electrons, but in the fact that there can be hydrogens and things like that in there, and that the electrons are shared between them, that means that the total amount won't be a multiple of 8 necessarily. Because, so for example, if you have 2 fluorines interacting with each other, right? Each fluorine has how many valence electrons? 7, which means the total number of electrons is 14, right? So that's not a multiple of 8 in that case. They'll be even, right? Because there has to be 2 electrons shared between atoms. But they're not going to necessarily be a multiple of 8.
So it won't satisfy the octet rule?
It'll still satisfy the octet rule, but remember, each one is donating an electron to the other to share around them. So we haven't added any electrons to the structure, right? We've just started sharing some of our electrons so that we satisfy the octet rule, right? It's like there's a little bit of overlap between them, but we haven't added any electrons to the molecule when we made it. Tiffany?
Instead of spreading out, for carbon, instead of spreading out the electrons, did you just put 2 on each side and that would give them the double bond?
If you knew, yeah. So like as you get better and better at this, like you don't have to start off with that exact Lewis dot structure. Like for example, usually when I do this example, I'll draw it even just, if I draw it like this, I'll draw oxygen like this, for example. And the reason I draw that is so that I don't have to, in this step right here, I don't like how the arrows go on opposite sides of the bond. I draw it like that because I know I'm gonna create 2 bonds. And as you do and draw Lewis structures more, you'll know, okay, well I can just start with 2 electrons on each side and it's easier for me to draw that and connect the dots that way. So yeah, once you get more comfortable with it, yeah, you'll definitely be fed. This is a very tedious process to go through for everyone, but I guarantee you if you start from drawing Lewis structures like this, that you won't ever make a mistake because you're directly drawing where the electrons are going. But you could do that if you knew beforehand, but it's easy to make mistakes that way too. Any other questions? Good questions. Anai?
Do dots have to be oriented like that, or can they be like Two on top and two on the bottom of like oxygen.
So, oh yeah, so in the end,
Yeah.
yeah. So actually, that would be the more correct way to draw it. Would be the dots opposite to each other, because these two electrons, when they're together, they form a lone pair. Lone pairs don't like to be next to each other because they're both negatively charged, right? Electrons, they want to spread out, so they will spread out far apart from each other. I'm not going to grade you on right now, especially because we're just talking about Lewis structures. I'm not going to grade you on where your dots are around it. You know, the only thing that would maybe like warrant some points is if you drew like all 6 electrons on one side or something like that. But that would look funky from the start. So hopefully that isn't your first intuition to go to there. But in terms of drawing the actual Lewis structure, that would be the most accurate way to draw it. Yeah. All right. Any other questions on this one? Okay, so based off of time right now, I'm probably not going to get to molecular shape or intermolecular forces for the next exam. So this is where we'll stop. So we're just going to spend the rest of the time kind of just going over some practice for Lewis structures. But we're not going to go over intermolecular forces or shape. We'll do that for the quiz after this exam. All right, so here's an example of a charged molecule. I'm not going to give you an example like this on the exam. So what I'm going to do is I'm going to skip over this one, and then you guys already have seen that one. That's another charged one. I'll give you guys an example. Let's look at C or H2, CH2O. This is called acetone. Right, so this isn't something that I'd ask you guys to name. Why? Because it's not a binary compound, right? I can't, you wouldn't know how to name this given the tools that you've been given so far. This molecule has a common name. All right, so see if you can draw the Lewis structure for this. The structure first, right? So what's going to go in the center here? Carbon, right? Because hydrogen likes to be where? On the outside, and then oxygen is, how can we know oxygen is in the center? Yep, it's less metallic than carbon or more electronegative, right? So it's more electronegative. So oxygen is also going to go on the outside. We can draw it like this if we want to. And how many valence electrons does oxygen have? 6, right? Because it's in which group? Sam?
I wanted to ask, is like being metallic and electronegative like inversely related?
Yeah, so the same way that ionization energy and electronegativity follow the same trend, atomic size and metallic character follow the same trend, and electronegativity is the opposite trend of that.
Okay, I see.
And so for the next exam, one of the things that I said you can have on it is your lab-made periodic table. So on Monday, what we're going to do is make sure you come to lab on Monday, is I'll print out some periodic tables for you, and you're going to take notes to remember the trends on there, oxidation numbers, valence electron, things like that, right? So you can use what we make in lab on Monday on the exam, right? So you'll have a periodic table, except it'll be a little bit more organized to your liking, displaying the trends, so you don't have to necessarily memorize how they work, right? I want you to be able to apply them, not necessarily memorize them. All right, and how many valence electrons does carbon have? 4, right? So 4 dots around. Carbon, what about each hydrogen? 1, right? So that's our Lewis skeleton structure. What's the next step we have to do? Connect them, right? So each element donates how many valence electrons to a bond? 1 valence electron each to form 2 electrons within that bond, right? Now those 2 electrons are circling both of those elements together, right? So that goes to 1 there, 1 there, 1 there, and we get something that looks like this. And so now we need to check what? Check the octet rule. And let's check hydrogen first, right? Hydrogen has how many dots? 0 dots, which means how many electrons and dots? 0 electrons. How many bonds does each hydrogen have? 1 bond, which means it has how many 2 electrons? 2 electrons. So it has 2 electrons total. Is hydrogen happy with 2 electrons? Yep, hydrogen is happy with 2 electrons, so that's okay. Let's check carbon now. Carbon has how many dots? 1 dot. How many bonds? 3 bonds. So how many electrons in bonds? 6 electrons. How many in dots? 1 electron. So how many electrons total? 7 electrons. So does it satisfy the octet rule? Nope. And what about oxygen? How many bonds? 1 bond. So that's 2 electrons. How many dots? 5 dots. That's 5 electrons. That's 2. So how many electrons total? 7 electrons. Does it satisfy the octet rule? No. That means that we have to redistribute electrons in or out of bonds between this carbon and oxygen now, right? Because they both don't satisfy the octet rule. And so how are we going to do that? Right, we see we have this 1 electron here from carbon. It can share that with the oxygen, and the oxygen also has 1 spare electron to then share with the carbon as well. So let's try see if we put both of those into a bond between the carbon and the oxygen and see if that then satisfies the octet rule. Hydrogen we're not going to do anything with right now because we see hydrogen is okay where it is. All right, so we do that. We get something that looks like oxygen and the 2 hydrogens right there. So now let's check the octet rule again. For carbon, how many bonds do we have? 4 bonds around it total, right? How many bonds total do we have around carbon? 1, 2, 3, 4. 4 bonds attached to carbon means we have how many electrons in there? 8 electrons, and how many dots? 0 dots. So there's 0 electrons from that. So how many electrons total? 8 electrons. So that satisfies the octet rule. And what about oxygen? How many bonds do we have around oxygen? 2 bonds. So that's how many electrons? 4 electrons. How many dots? 4 dots. So that's how many electrons? 4 electrons. So we have how many total? 8 electrons. So we satisfy the octet rule. That means that this is our valid structure for formaldehyde. So using this, even though this is an asymmetric molecule, right, we have hydrogens, oxygens, and carbons in this. Using just our stepwise method, we can go through and make sure that we end up with the correct Lewis structure. Right, and this is actually the structure of what formaldehyde, as I incorrectly called acetone, looks like. Question, Center?
So when you're doing the skeleton, are you only looking at the valence electron?
That's exactly right. When you draw the Lewis symbol in the skeleton, the dots are only the valence electrons.
And then when you're done,
You're looking at all the electrons that are around it now.
that's why I was confused.
Yeah, so that's why it isn't a multiple of 8, is because you can have any combination of the number of valence electrons. But in the end, everything needs to either satisfy the octet rule or the doublet rule.
Okay, thank you.
Yeah, so the dots only represent the valence electrons, right? So cesium, for example, right, number 55 on the periodic table, how many electrons does cesium have total? Not valence electrons, but total. 55, right? Because it's a neutral element. It has how many protons? 55, which means it has the same number of electrons. So it's 55 total. We're not going to draw 55 dots around cesium because those core electrons don't affect how it bonds. We only care about the valence electrons. So cesium is only going to have 1 valence electron. Why? Because it's in what group? Group 1, right? So that's why we only care about the valence electrons in the Lewis symbols, because those are the ones that determine how we bond to other elements. Why? Because we want to reach octet rule, so we look like a noble gas, right? And that's where we're going to be most stable. Right, so Lewis dots are only the valence electrons. And how we share those gives us the actual molecules themselves. We're not talking about shape just yet. You can see the shapes kind of starting to form, but this is really how are the atoms connected to each other, not necessarily what the shape is yet. We'll learn about that next week. Good questions. Any other questions on Sam?
It's kind of off topic, but why is it called formaldehyde already?
So this functional group here, right? Let's say this is any other, it can be attached as many other carbons. When you have a C double bonded to O like that and a hydrogen bonded to it, that's called an aldehyde functional group. If you go into organic chemistry, you'll learn all about it. This one is, you know, the simplest aldehyde you can have because there's no other carbons here, right? Just bond to another hydrogen. The form is just because the when they discovered functional group aldehydes, they hadn't come up with the standardized naming convention for organic molecules yet. No worries. All right. So what are some things we're looking at when we're looking at Lewis structures? Are the correct number of electrons present in the structure? So again, we can go over next week, we'll maybe talk about looking at some of the charged atoms, right? So those aren't very good for quiz questions or exam questions, but makeup quizzes, those are good questions, right? Because they're kind of hard. And then is the octet rule or doublet rule satisfied for everything, right? So those are the main things we're looking at when we're looking at or drawing Lewis structures. And so there's another question I'll ask you guys. So if instead of oxygen here, I had sulfur, how do you think that would change the compound? All right, so what if I had CH2S instead of CH2O? It would be the same except what?
The S would be instead of the.
Except instead of oxygen here, we would have a sulfur. So does anyone have any idea why sulfur might look the same? Thioformaldehyde might be the same, huh? Because of the same valence electrons, right? And so that's what I mean when you do this enough, you'll start seeing the patterns. Well, if I just take this molecule and I change it with any element that's in that same group, it's going to form the same type of connectivity that that element does. Why? Because the valence electrons determine that, and the groups are organized by the valence electrons, right? So if you know what ammonia looks like, right? So if I go to the next slide here, and I look at ammonia, this is what the Lewis structure for ammonia would look like. And now I want to say, well, what does pH3 look like? Which you can name now. So how would you name pH3? It would be phosphorus, tri, because we have 3 and it's a covalent compound. Hydrogen, what do you think it becomes? Hydride. Hydroxide would be if it's OH minus, right? So this would be hydride. Phosphorus trihydride, right? If you didn't go through and draw the Lewis structure for phosphorus trihydride, how do you think the Lewis structure would look like if we know the Lewis structure for ammonia?
You just sort of replace the N with
Yeah, this would just look like PH, like that, because it has the same number of valence electrons as nitrogen because it's in the same group. All right, so we start recognizing patterns like that. It'll help us kind of determine what these Lewis structures are going to be before we even go through the process of drawing them. You still want to go through to make sure the octet and everything is satisfied. But that's why the groups are organized this way, is because the bonding characteristics or bonding personality of each atom is the same if it's within a certain group. Or we can right now, we can think of them as being the same. All right, so just some patterns to kind of keep track of here. Okay. So here we have, well, the exact example that I gave you. So for this Lewis structure, we know what the correct Lewis structure is, but why would this Lewis structure be wrong? Yeah, if we look at carbon, how many electrons are around carbon? Right, we have 3 bonds, which is 6 electrons, and how many dots? 0 dots, so we have 0 electrons, so we have 6 electrons around it, right? So this doesn't satisfy the octet rule. That's one reason that it could be wrong. if we counted the total number of electrons, they would be fine here. And we know that from our previous example that this looks like, this is what the structure of formaldehyde looks like. Okay. So what about for this compound? Why might this... we haven't talked about formal charge yet, so let me talk about formal charge for a second. So if we're dealing with charged compounds, right, we can calculate the actual charge on each of the individual atoms. So that's why I skipped over them before, right? So this would be a Lewis structure example of something that has a charge on it, right? So when we have a Lewis structure, we have the number of valence electrons minus the number of dots plus the number of bonds times 2. And this gives us the formal charge on the atom. Is 8 minus number of valence electrons. So this should be done. This should be, sorry, I did it backwards. This will be, where did my lasso go now? Where? Number of bonds minus the valence electrons. And so when we're calculating the formal charge, when we talked about things like polyatomic ions, so we have polyatomic ions, which are going to be ions are charged molecules. And polyatomic just means more than one atom. These are molecules that were covalently bonded to each other, but they still had a total charge on there. And so in the molecular structure for these, we have covalent bonds, but we still have a charge floating around somewhere. And this is calculated by looking at the formal charges on each atom. And so the formal charge tells us which atoms in the Lewis structure are actually going to be charged. So this tells us which atoms in the Lewis structure are charged. And so we don't have time to go through that today, so we'll start off with that on Monday and then get into molecular shape. But when we look at polyatomic ions, which we know how to name and how to use them in ionic compounds, we're now going to determine what is the actual structure of these based off of drawing the Lewis structure for them. Where is the charge located, and what atoms can we put the charges on? All right, so we'll stop there for now.